This is lesson 7.4, the equilibrium law. So homogeneous equilibria is when the reactants and products are all in the same phase. So they're either all gases or all solutions. And there's lots of problems we can do with homogeneous equilibria. So the first type of problem is when the problem asks you to calculate Kc from initial equilibrium concentrations. So to do this, you have to make sure that you always write the Kc expression, or the equilibrium expression. So here's an example. Hydrogen can be prepared by the combination of carbon monoxide and water at 500 degrees. At equilibrium, the concentrations in the reaction mixture were found to be CO 0.15 molar, H2O 0.0145 molar, H2 0.2 molar, and CO2 0.02 molar. Calculate the equilibrium constant for the reaction at this temperature. So the first thing that you're going to do is write a balanced equation. So carbon monoxide combined with water goes to hydrogen gas plus CO2. And this equation is already balanced. So we're going to write our Kc, so products, hydrogen and carbon dioxide, over reactants, carbon monoxide and water. And they give us the equilibrium concentrations. So all we're going to do is plug them in to find Kc. So H2 is 0.2 molar, CO2 is 0.02 molar, CO is 0.15 molar, and H2O is 0.0145 molar. And when we solve for Kc, we get 1.84. And there's no units for Kc. The second type of problem asks you to calculate values for equilibrium concentrations from initial data and equilibrium data. So to do this, there's a few steps. The first thing you have to do is write the balanced equation. And then next you're going to set up what we call an ICE table. So the I stands for the initial concentration, the change stands for the amount that reacts to reach equilibrium, and the equilibrium is the concentration present at equilibrium. Then the third step is that you'll write the Kc expression and substitute the values from the ICE table in. So here's an example. A student placed 0.2 moles of PCl3 and 0.1 moles of Cl2 in a 1 decimeter cube flask at 250 degrees Celsius. The reaction, which produced PCl5, was allowed to come to equilibrium, at which time it was found that the flask contained 0.12 moles of PCl3. What is the value of Kc for this reaction? So the first thing that we're going to do is write a balanced equation. So PCl3 plus chlorine goes to PCl5, and it's in equilibrium, so remember your double arrows. We need an ICE table, so all you do is write the letters ICE, and it does have to be set up exactly like this. Now the flask is 1 decimeter, so fortunately all of the molarities are just moles over 1. So 0.2 moles over 1 is 0.2 molar, 0.1 mole over 1 is 0.1 molar, and of course we don't have any starting PCl5, so the initial concentration of that is just 0. But we know from the question that at equilibrium it was found that there was 0.12 moles of PCl3. So 0.12 moles over 1 liter or 1 decimeter cube is just 0.12. So that is our equilibrium concentration. So we know the 3 initial concentrations, and we know the equilibrium concentration of the PCl3. So the change to go from the starting concentration of PCl3 to the end must have been minus 0.08. And so we know that because it's a 1-to-1 molar ratio, the Cl2 also must have used 0.08. And again, because it's a 1-to-1 ratio, the product must have gained 0.08. So when we subtract, we find the equilibrium concentrations of Cl2 to be 0.02 and PCl5 to be 0.08. Now, since we have our equilibrium concentrations, we can write our equilibrium expression, and all we're going to do is plug in our equilibrium concentrations to the expression. So 0.08 for PCl5 all over 0.12 for PCl3 and 0.02 for Cl2. So that gives us a value of Kc equal to 3, 3, so 33. The third type of calculation that you'll be asked to do is to calculate the equilibrium concentration from Kc. So for the reaction CO plus 2 hydrogen goes to CH3OH, they give you the Kc of 0.5 at 350 kelvins. If the concentrations at equilibrium are CO 0.2 molar and H2 0.155 molar, what is the equilibrium concentration of CH3OH? So, in this problem, they give you Kc, but we should still write the Kc expression. So Kc is equal to CH3OH all over CO and H2 squared. And remember, those are all concentrations. So we know Kc is 0.5, so we can plug that in. We don't know the concentration of CH3OH, so we're going to leave that. But we do know that CO has a concentration of 0.2 molar, and H2 has a concentration of 0.155 molar, but remember that's squared. So now all we have to do is plug into our calculator and solve for CH3OH, and you should get a concentration of 0.00240 molar, so moles per decimeter cubed. The fourth type of problem is where it gets trickier. So the fourth type of problem involves calculating the equilibrium concentrations from Kc, knowing only the initial concentrations. So again, we're going to use ice tables here. So here's an example. The equilibrium constant Kc for the reaction SO3 plus NO goes to NO2 plus SO2 was found to be 6.78 at a specified temperature. If the initial concentrations of NO and SO3 were both 0.03 molar, what will be the equilibrium concentration of each component? So this is trickier because they don't give you any of the equilibrium concentrations. So again, you set up your ice table, and we know that they were both 0.03 to start with, and we didn't make any products yet, so that's 0. What we don't know is the change. So if we say that the change is X, we know that the reactants will decrease by X and the products will increase by X. So that the equilibrium concentrations will be 0.03 minus X, 0.03 minus X, X, and X. Because 0 plus X is just X. Now what we can do is write our Kc. So Kc equals concentration of NO2 times the concentration of SO2 divided by the concentration of SO3 times the concentration of NO. And they give us Kc 6.78. So all we have to do now is sub in our equilibrium concentrations. Now, this problem becomes complicated because to solve for X, you'll see that what you would have to use is our special formula, the Pythagorean theorem. However, there's a shortcut. So if you put the Kc in, 6.78, you'll notice that if you were to take the square root of both sides, so the square root of 6.78 and the square root of everything on the right, you would get the square root of 6.78, so 2.60. Square root of x squared is x, and the square root of 0.03 minus x squared is just 0.03 minus x. Now it makes it very simple for you to solve for x. So you're going to cross multiply, and when you finish, your x will be equal to 0.0217. But remember, the x is just the change. So at equilibrium, the change in the concentration of reactants was 0.03 minus x. So our new equilibrium concentration of SO3 and NO is going to be 0.0083 molar. So that's SO3 and NO. The equilibrium concentration of the products was just X. So 0.02 or 0.022 molar is going to be the concentration of NO2 and SO2. Do not forget to go back and find the equilibrium concentrations. Many people leave this as just the X, and that is wrong because that's not what the question is asking. The last type of equilibrium problem that you'll be asked to solve is one where you have to calculate the equilibrium concentrations when Kc is extremely small. So normally this is when Kc is less than 10 to the negative 3. So here's an example. The thermal decomposition of water has a very small value of Kc. At 1,000 degrees Celsius, the Kc is only 7.3 times 10 to the negative 18th. The reaction is 2 waters goes to 2 H2 plus O2 gas. A reaction is set up at this temperature with an initial H2O concentration of 0.1 moles per decimeter cube. Calculate the H2 concentration at equilibrium. So again, we don't know our equilibrium concentrations, so we will be using an ice table. We know the initial concentration of water is 0.10, and the products are 0 starting out. We don't know the change, but you can notice in this problem the change is going to be minus 2x because there's 2 water, plus 2x for hydrogen because there's 2 hydrogen, and just plus x for oxygen because there's only 1. So our change is 0.10 minus 2x, 2x, and x. Now because Kc is very, very small, that means that not very many products are formed. So what you're going to do is you're going to pretend that this change is so small that it doesn't matter. So instead of using 0.1 minus 2x, you're just going to say it's 0.1 because the change is so small that it's negligible. So we write our Kc expression, H2 squared times O2, all over H2O squared. And then we plug in. So Kc is 7.3 times 10 to the negative 18th. H2 is 2x squared, O2 is x, and H2O is 0.10. We ignore the minus x part. Because we can ignore the minus x part, that makes it much easier to solve for x. If we didn't ignore that minus x, then it would be much more difficult, and we'd have to use b squared plus or minus square root of 4ac, yada yada. So when we solve, x equals 2.632 times 10 to the negative 7, and they want to know the H2 concentration at equilibrium. So remember, the change is 2x, so you need to multiply that x by 2 to get the equilibrium concentration of H2, which comes out to be 5.3 times 10 to the negative 7. So Kc can be manipulated for a variety of different situations. So if you reverse the reaction, what you're going to do to Kc is take the reciprocal. So the Kc for the reverse reaction is the reciprocal of the Kc for the forward reaction. If you double the reaction coefficient, so if you double everything in the equation, you're going to square the Kc. If you half the reaction coefficients, therefore, you're going to take the square root of Kc. And if you add two reactions together, you're going to multiply the Kc for the first reaction times the Kc for the second reaction.